All right, so on this PowerPoint, what we're going to do is pick up on a few last topics on Chapter 16 that I want to make sure we're adequately covered. You should be on page 14 of your lecture notes, and near the bottom you'll see a space at the bottom of page 14 for sample exercise 16.18. And you can put the solution for this in here if you wish, or take time later to look at it in your textbook. One of the things we didn't talk about on hydrolysis is what to do if you have a solution that has an amphiprotic ion, meaning that it could act as either an acid or a base. And so you can see in the two equations below here and right below it, we've got acting as an acid, this HPO4 2- ion donating a hydrogen. They omitted water from the equation, which I would fault them for. And here it is acting as a base, accepting a hydrogen, turning from HPO4 into H2PO4. So we have to find the one with the larger equilibrium constant to find out who is going to be acidic or basic, which one is going to happen. And it depends upon the Ka and the Kb. So you're going to need a Ka table. We'll be working with phosphoric acid because you'll notice there isn't an H2PO4 listed, but if this is the Ka for H3PO4, then this is the Ka for H2PO4, and that is 6.2 times 10 to the minus 8. Notice I'm using the ion product constant for water method to find the Kb of HPO4. There is no Kb table, but if I take 1 times 1 times 10 to the negative 14 is equal to Ka times Kb, if I solve for Kb, it ends up being the ion product constant for water is divided by the Ka for the one we identified up here, 6.2 times 10 to the negative 8, and we find a Kb of 1.6 times 10 to the negative 7. So that Kb is much bigger than the Ka, so if you put this ion into water, it's going to undergo basic hydrolysis. And so you can find that again as sample exercise 16.18 in the 13th edition of the textbook. Now moving on a little, there were a few things that we had to cover to make sure you understand completely. And the thing that we want to look at next is, feel free to write inside your lecture notes if you wish. We're now going to kind of go in order to pick up the topics that we missed. But you can notice down here that we have an iron ion that's been surrounded by 6 waters. And interestingly enough, this acid hydrolysis of metallic ions only happens if you have metals that have charges of 3+ or higher. What happens is, because the iron is a 3+, it attracts the negative ends of water molecules towards itself. And interestingly enough, if I take 3 times 2, the number of water molecules that surround this hydrated cation is equal to 2 times its charge, or in this case 6. So now what we've got is water coming from a different source that sees this little hydrogen hanging out there. And because the iron has a positive 3 charge, and because the oxygen is so electronegative, there's a strong attraction between these guys, which weakens the bond right here. And a water molecule cruising in can snag that hydrogen, and turn it into H3O. And what you're left behind with is no longer an iron with 6 waters, but 5, and then a little hydroxide hanging out here at the end. So metallic ions with a 3+ charge or higher have much higher Kas when they are dissolved in aqueous solutions than metallic ions with lower charges. So be ready to see something about that on your test. Now we're also going to need to be ready for on the test some questions that say, which one of these acids is stronger? And so the 3 factors that influence acid strength are the polarity of the HA bond. And this A guy here is just whatever anion is attached to hydrogen. And when you have an acid, it needs to be a polar bond, and the polarity is going to need to point from the hydrogen towards the A atom, the more electronegative atom, if it wants to act as an acid. So you're going to have partial positive on hydrogen atoms, and you have to have partial negatives on the conjugate base or anion to which it is attached. The second factor that is influencing bonds, the ability of an acid to turn into an acid or its strength, is bond strength. And basically you know that the weaker the bond is, the more readily it is broken, and the more readily you can get rid of a hydrogen ion, then you have a stronger acid. This third concept, stability of the conjugate base or the anion, we'll talk about when I get some images up here. Now, this particular image cut off a little bit of the graph here, but you can also see this in your PowerPoint notes. When we refer to a binary acid, this is an acid made of hydrogen and one other element. And potentially all the substances that you see in this upper right corner of the periodic table from compounds formed from those elements could potentially be acids. And let's take a look at how we can figure out if they are or are not acid, and which factor, your bond strength or your bond polarity, is going to influence the strength of the acid the most as you travel across a period and as you go down a column. So first off, I'd like you to just notice here that when a carbon is attached to a hydrogen, this isn't an acid anymore. This time the polarity of the bond is backwards from what it's supposed to be. It'll be pointing towards the hydrogen as being more electronegative, and so of course that makes things like CH4 or silicon tetrahydride, this is methane, to be neither acid nor base. If I move over one more spot over here onto the periodic table, now what we're going to look at is NH3 and PH3, and these are, I hope you now know, are weak bases. These are substances that are trigonal pyramidal. They'll have an unshared pair of electrons at the top of the little pyramid on the N and on the pH. They're very weak bases, and they're not acids. What we're having as we move across from left to right, the acidity of acids within a period is going to increase as it gets more and more electronegative. So these two guys right here are acceptors of hydrogens, not donators of hydrogens. Now water is a little hard to explain because it's both acting as an acid and acting on a base, depending upon who's in the neighborhood. So let's look at the example of hydrogen sulfide, or when you dissolve hydrogen sulfide in water, you make hydrosulfurous acid, I think is its name. And then of course you're all familiar with hydrochloric acid. So one of the factors that within a period that increases the strength or the ability of a substance to act as an acid is increasing polarity. So if I compare chloride ions to sulfide, chloride is much more electronegative. We have that thing where we draw away the electron density closer towards the chloride or to the sulfide, but more strongly so in hydrochloric acid. That makes the hydrogen ions a little bit more free to be lost, and that's how you can increase the strength of an acid. So within a period, going from left to right, an increase in electronegativity, which of course you know occurs as we travel left to right, makes the bonds more polar, makes it more easy for hydrogens to be removed, makes them a stronger acid. When we look at the other trend though, going from top to bottom, now we have to look at another factor, and that has to do with the strength of the bond. So it's a little covered up here and I can't really show it, but I can explain it, and I know you can see it on your paper. As we travel down a column, let's pick these guys here, you hopefully have memorized that HCl and HBr are the strong acids. Hydrofluoric acid in its period is the strongest acid, but it's still a weak acid even though it's very polar, and let's see why. As I go down the column on the periodic table, the skill that you learned about the size and ionic trend the trend in ionic size is very important. As I jump down from one row to the next, I'm adding another energy level worth of electrons. So atoms get bigger and ions get bigger going down. The bigger the atom, the longer the bond between it and hydrogen, the weaker it is and the more easily broken it is. So acids will increase in strength as we travel down a column in the periodic table because the bonds get longer and therefore weaker, and the ability to lose a hydrogen ion gets greater. So those are the factors of polarity and electronegativity influencing your strength of acid left to right. and the weakness of the bond as you go down due to increasing ion or atom size as you travel down a group on the periodic table. I think that's the big points on ranking these guys. So now let's take a look at how you can figure out, comparatively speaking, what the strengths of acids are relative to each other. So we're going to take a look at oxyacids now. And an oxyacid, as you can see, is a central atom that's got OH groups and possibly additional oxygens on it. So here's my central atom. And in this particular case, Y is going to be a nonmetal. If you had a metal attached to an OH, of course, I hope you know by now that's a base, not an acid. But if this is a nonmetal attached to an OH, anything that can weaken the OH bond and make it easier to pluck away this hydrogen to jump on a nearby water is going to make it a stronger acid. Well, what makes it a weaker bond right here is increasing the electronegativity of this nonmetal atom to which the OH is attached. So, of course, if I compare chlorine to bromine to iodine, the most electronegative of the set is chlorine, and therefore it shifts the electron density over this way towards the chlorine. Another way to say that is you're making its conjugate base more stable, but you can also visualize it as this bond here between the hydrogen and the oxygen becomes more polar, and the hydrogen is more easily plucked away. So as the electronegativity of the nonmetal to which they are attached increases, then the acidity will increase for the same structure that you see here. If you take a look at the second kind of oxyacid, now you notice that all four of these examples at the bottom of this slide are basically with chlorine, my nonmetal atom, to which an O is attached. But every time I attach another oxygen or another, or even one more to go from hypochlorous to perchloric, you can see that the acids start out weak and become very strong. The more oxygens that you add to an oxyacid, the greater the acidity of the acid that is forming. So there is an example about this in sample exercise 16.20, which we will work through right now. And you can also find that in your textbook. Expect a question where you would be asked who is the stronger acid, who's the weakest acid, or rank them. One more time, adding more and more oxygens draws the electron density away from this bond right here. It makes the conjugate base more and more stable, more likely to break the hydrogen off from the oxygen, have it go find a water and form hydronium. Another way to say that, which I'm not going to hold you to, is that if you increase the oxidation number, then the acidity of the substance will also increase. So another thing that happens is that you sort of spread out the negative charge, and that increases the stability of the conjugate base. So here would be a typical question, and this is from sample exercise 16.20, the solution for which is in the textbook. If you're at a point in your lecture notes where you see an empty spot where you could plop in the sample exercise, go ahead and do so. There are two examples here, and in the upper right corner I can have a variety of substances that all have hydrogen in it, but I can jump right onto this guy because the hydrogen's in the wrong spot, first of all. This is a low electronegativity element, potassium, and in fact this is ionic, and that's not a hydrogen ion, that's a hydride ion. And so what can happen in this particular case, the hydrogen, if I was going to try to draw a bond dipole, which I really shouldn't, the more negative would be the hydrogen. So that can't act as an acid at all. I'm looking at the next two guys and I'm seeing, well, bromine and selenium are kind of over in here. So maybe these guys, well, I know the hydrogen bromide is going to be the strongest acid if you memorize them. So let's take a look at the next example, ASH3. So here's arsenic with a 2.0, and here's hydrogen with a 2.1. Same situation, we actually have a more electronegative charge on the hydrogen, so it's not going to become, as you will see here, a polar bond, it's a non-polar bond. So it's got very little tendency for it to donate that hydrogen. When we get to the selenium and to the bromine and compare their electronegativities, let's pop back there real quick. On the electronegativity chart or on their location, you can see that bromine is much more electronegative. It makes a bond with hydrogen much more polar than it would with, say, selenium. So definitely the strongest. Here's my second runner-up. I know that my weakest was this potassium hydride, so the second weakest, if you want to phrase it that way, must have been the ASH3. And that is the answer that you can see here. Remember, if you're confused, the arrow is pointing to the smaller value, if that helps you. Now you had 3 other acids to compare to each other, and they were H2SO4, which I hope you recognize as being a strong acid to begin with. And then these 2 guys are exactly the same, except this one's got one more oxygen. So I know whatever the lineup's going to end up being, my H2SO4 has to be my strongest. But between these 2 guys right here, the one with only 3 oxygens is a weaker oxyacid than the one with 4. I know that much for sure. So now we just need to compare the electronegativity of sulfur to selenium. And when I pop over here to the periodic table, sulfur is slightly more electronegative. So this H2SO4, it's actually a polyprotic acid, but we'll just look at the first hydrogen that comes off. It is going to be a stronger acid because the sulfur is more polar. It draws the electron density closer towards itself, weakening the bond with the hydrogen. And it does that better than selenium does because selenium is less electronegative. So if sulfuric acid is the strongest acid, then the second strongest would be the we lost him here, H3SO4, I believe it was, and then the, H2SeO4, and then the weakest would be H2SeO3. Okay, so look for 1 or 2 questions about that. Maybe see 1 question about this guy. It's called a carboxylic acid, and it should sound familiar because you did it last year when we did the esters lab. Organic acids are acids that have a carboxyl group, a C double bond O, OH, attached to a ring or chain of carbons. Down here, this is ethanoic acid. Sorry, I had to count how many carbons in there to remember my organic chemistry. Not shown right here is the hydrogen atom, and so it's been pulled away by hydronium. And the reason it did is because it's got electronegative oxygen, which is pulling the electron density away. And notice you could have a little resonance tail end to this guy. When you have resonance, it smears out the electrons around that little part of the molecule, and it stabilizes or makes the leftovers after the hydrogen leaves more stable, and therefore makes it an acid. So carboxylic acids don't have to be attached to a chain of carbons. You could have a carboxyl group attached to a, hopefully you know this is a benzene ring, a hexagon of 6 hydrogens, 6 carbons attached in a hexagonal shape with various other structures that can come off, and we can show it has resonance because it has alternating double and single bonds. And so that's called benzoic acid. Finally, there's a very strange sort of definition of an acid. The Arrhenius definition of acids and bases was old, and that's the one that said acids make hydrogens in solution and bases make hydroxides. The better definition of acid and base that we have predominantly focused on is the Bronsted-Lowry. Acids are donators of hydrogens, bases are acceptors of protons or hydrogens. But the third definition, the Lewis acids, are easier to see with a picture. But we'll start with the notion that Lewis acids are electron pair acceptors. Check out the picture. So if we have somebody like NH3, it's got an unshared electron pair right here. And a electron-hungry hydrogen ion, a proton, would love to latch on here to join up with ammonia to make the ammonium ion, NH41+. So that's how the ammonium ion forms in solution. Our definition is a little bit more clear down here at the bottom. We're going to find a Lewis base as the substance that has an electron pair to donate, and a Lewis acid as the substance has an electron pair that it wants to receive. And of course you know that BF3 is an electron deficient atom, boron is. It makes a trigonal planar molecule that is electron deficient. So it wants that pair of electrons. So the Lewis acid is the one that is accepting this pair of electrons, making sure our definition is correct, and the Lewis base is the one that is donating it. And you might see that in a trivia question. Don't hardly use it at all. That's it. Hopefully you can use this last PowerPoint and your summary of concepts that are important in Chapter 16 to study for your exam. Take care.